Okay, on to the stones. Well, stony meteorites are very complex. They're more complex than the irons are, I think you would have to say. But there are two major groups, what we call chondrites and achondrites. 86% of all of them are, of all meteorites are chondrites, 8% achondrites. Each of these has numerous subgroups based on the composition, but there are three subgroups that are also based on their origin, that is, where they came from. For the most part, these come from asteroids in our asteroid belt, but not quite all of them. And I'll talk more about that in a little bit. Here's three stones. Buzzard Coulee here from Saskatchewan. Buzzard Coulee fell in 2008. Chelyabinsk 2013. And Cameldonga there in Australia was 1969 when it fell. It's an achondrite, and yet it does not look appreciably different from the other two, which are both chondrites, and though not identical, they're fairly similar to each other. So we cannot identify the type of stony meteorite from an outside look either. Now, when we go through these pictures, we'll see that though some of the stony meteorites do have the thumbprints, the regmaglyphs, some of them don't. One piece of a particular meteorite fall might have the regmaglyphs, and the next piece might not have them. But overall, every iron, when it falls, has got regmaglyphs. Not all stones, when they fall, have regmaglyphs. Well, what are these chondrites I'm referring to? Well, chondrites are named chondrites because they contain small objects that we call chondrules. The picture up over here is trying to represent these. Chondrules are small objects, more or less circular in outline, more or less spherical in 3 dimensions, though sometimes they're angular and broken, but usually they're pretty roundish. They are made of a mineral, mostly made of a mineral we call olivine, which is a mixture, a compound, chemical compound, made of magnesium, iron, silicon, and oxygen. Though they can be made of other things. Some are also made of pyroxene, a chemical mixture very similar to olivine, but not quite the same. And then there are a couple of other minerals that occasionally show up in chondrules. Well, olivine is an important earth mineral as well. We'll take a closer look at it in the next slide. But chondrites, by far the most common type of meteorite, it's 86% of them, but they're extremely variable in the proportion of chondrules they contain, in the size of those chondrules, and in also the amount of iron and some other things about them. The picture on my far right these are to the same scale, contains a fairly large chondrule, just about in the middle, almost a centimeter. That's fairly unusual to find them that big. They're typically not more than 3 or 4 millimeters. And the very smallest ones on that cut face that you see in various places wouldn't be more than about 1 millimeter. The grayer looking specimen more immediately to my right, well, in the far right-hand corner here, that silvery stuff is iron. There's almost none, just a little bit. We can't even see it in the other picture. The chondrites in here are these small objects you see up here. So 1 to maybe 3 millimeters in diameter. Some of them are white, some of them are gray. The colors can vary depending on the ratio of iron to magnesium in the olivine. Well, we're done with the chondrules, though again you can see them in the picture on the far right. Some very nice chondrules. And you can't see with the naked eye any metallic iron in that picture. There's some there, but you have to look with the hand lens reading glasses or under the microscope you could see it. This next one is a bit rusted, but the iron is all the shiny stuff. And then it's quite patchy rust. There are chondrites as well, stuff up in both the corner closest to me and the far corner further away over there. There are some yellowish looking chondrules. The next picture is a different meteorite closer to me. You can't even make out any chondrules anymore. It's so badly rusted just spread over everything. But because the surface has been polished, you can see the nice shiny iron in it, perhaps 15% iron in this case. So these would, depending on the amount of iron that you can see is metallic iron, and depending on the amount of iron that's in chemical compounds like the olivine or the pyroxene, we can classify meteorites on the chondrites on the basis of the amount of iron they've got. The achondrites contain no chondrules. These make up about 8% of all known meteorites. Some contain some metallic iron, not as much as on average as the chondrites, and nowhere near as much as the chondrites that are most rich in metallic iron. But some chondrites have absolutely no metallic iron in them at all, such that perhaps 3 to 4% of all meteorites will not be attracted by a magnet. And one of the things you may have heard about meteorites, well, grab a magnet, see if it attracts it. Well, of course, the irons do. Most of the chondrites will have enough iron to be attracted quite easily to even a fairly weak magnet. The achondrites, some will be attracted. In fact, one particular one will be highly attracted, but some of them won't be attracted at all. Some achondrites are rather similar to some earth rocks, particularly the basaltic lava that we find in Iceland and Hawaii. Similar, but not identical. In fact, the basalt that we find in some achondrites is usually light in color rather than black in color. And this is because of the chemical composition of another mineral, partly olivine and partly one called pyroxene. Again, changes color depending on the ratio of iron and magnesium. Now, the three groups of achondrites that I said were classified partly on where they come from. Indeed, some meteorites on Earth have come from the moon. They've been blasted off the moon at some unknown time in the past, perhaps stayed in orbit around the sun for a long period of time, but eventually spiraled in and hit Earth on the way. Martian meteorites, the same. We have Martian rocks blasted off Mars sometime in the distant past by a large asteroid hitting Mars, and then bits of Mars ending up on Earth. One of the largest of the asteroids, second largest one called Vesta, also is thought to be the source of one of the groups of achondrites. Pictures of some more stony meteorites, just so you can get a good look at them and get to understand some of the nature of the complexities. The one in the far right over here is a piece of the Buzzard Coulee, a 2008 impact just south of Lloydminster in Saskatchewan, close to the Alberta border. It was the biggest piece found, 14 kilograms. And you can see that part of it, well, there's a toonie down there for scale. You can see part of it has nice regmaglyphs, and part of it doesn't have any. And this is the way it is with the stones. The development of regmaglyphs is very uneven. There's another stony meteorite here, no regmaglyphs, some regmaglyphs, virtually none in this piece, None evident in that piece, none there, lots in this one. And yet this piece and this piece are part of the same meteorite, not part of the same fragment, but part of the same meteorite. This one, these four here are all achondrites. The four at the top are all chondrites. The one over here is a lunar achondrite, and it has gotten rusty and partly decomposed on while it's been on planet Earth. Notice that, as is the case with most chondrite meteorites, no matter that they've got this nice shiny black fusion crust, much like the irons, but they're gray inside, light to medium, even dark gray. But some of them aren't. There's the odd one that is dark reddish brown, and there's some we'll look at fairly shortly that are actually dark gray to black inside. But most of them are gray.